Hello everyone, welcome to my YouTube channel. Today I'm solving Leetcode question 309. Best time to buy and sell stock with cooldown. You are given array prices, where prices I is the price of a given stock on the I day. Find the maximum profit you can achieve. You may complete as many transactions as you like. That is, buy one and sell one share of the stock multiple times, with the following restrictions. After you sell your stock, you cannot buy stock on the next day. That is, you have a cooldown one day. You may not engage in multiple transactions simultaneously. That is, you must sell the stock before you buy it again. Example 1. The input prices is 12302. The output is 3. The ultimate transaction is you buy on the first day when the price is 1 and then sell on the next day to gain profit of 1. And then you have a cooldown for 1 day when the stock price is the highest, and then you buy it on the 4th day and then sell it on the last day to get a profit of 2. So in total you get profit of 1 plus 2 equals 3. The second example, prices equals 1, the output is 0. So how to solve this problem? So basically, let's think about the overall idea is, let's say, what is the current state and what is the next state? So basically, some of the idea is current state. You have the current state, and then you determine the next state. Why is that? Because let's say, if you just sell your stock, and then the next day you will have a cooldown. So basically, the overall idea is from the current state to determine the next state. So then how to solve it? So the first idea is actually to solve it using recursive solution. So have a recursive function. It may not be the optimal solution, or it may run out of time, but it's kind of a very basic and easy idea to start with, and then we can work on optimizing this solution. So first, let's go over the idea to solve it using recursion. So for the recursion, we must know what is the base case, and then from the current state to the next state, then what is the current state and what is the next state. So basically, the state, basically you are checking the prices. You are given the prices on each day. So basically, we for our recursive function, we have a function. We call this recursive function. Let's say recursive function for the day on the ith day. Let's assume you have a function I, and then from there you go to the next function. So current state going to the next state. So what can be the current state? So you can have a no transaction day. Basically, you perform nothing. You do not sell. You do not buy. So this is this state is whether or not you have a stock or not. Basically, whether or not you have a stock, you hold a stock, you have no transaction day. And then what other current states? So you can purchase a stock. So in that case, if you do not hold a stock right now, and you are not in cooldown period, in that case, you can purchase a stock. You can also sell a stock. You can sell a stock if you hold a stock. Basically, if you currently have a stock, then you can choose to sell that stock. So those are the three current states. And then what are the next states? So basically, before we are discussing the next state, you can tell from those conditions, knowing whether or not you hold a stock is super important because it determines whether or not you can sell a stock. So in that case, we need to add that status into our function, into our recursive function. Basically, the input for each recursive function is the I, indicates on the I state, and then hold is a Boolean variable indicates, okay, true or false, whether or not you hold a stock. So that's kind of the inputs for this recursive function. In that case, let's determine the next state given the current state. If you have a no transaction day, so the next day is you just move to the next day. That's the next state. And then you carry this hold indicator. So that's the next state. And then if you purchase a stock, basically if you purchase a stock today, and then you can go to the next day. And then in that case, your hold indicator is true. You can directly go to the next day because you can perform the transactions or have no transactions the next day if you have a stock. If you sell a stock, then the next day is a cool off period. So in that case, the next state is actually I plus 2, and then whether or not you hold the stock is false. Because for I plus 1, you know that immediately after you sell a stock, you have a cooldown period of 1 day. So in that case, from the current state, the next state, we are actually calling the function for I plus 2. So in that case, we start, so our starting point is the function. We start with the I state, and then hold equals false, and we do not have a stock. So that's our starting point. So basically, we call this function to enter the recursive function. So in that case, so what is the base case? So the base case is, let's say, if your I is out of the index, so basically if your I is greater than or equal to the length of prices, so in that case, you just return 0. Okay, so we kind of go over the idea of this recursive solution. So let's code this solution. So we define a recursive function called I, and then hold. We call this recursive function, and then first let's deal with the base case. If I is greater than or equal to the length of prices, in that case you just return 0. And then you consider the first condition, the first state is like no transaction. So in that case, you just call the function for I plus 1, hold. And then scenario 1, that's our scenario 1. And then scenario 2 is a purchase or sell. If your hold is true, if you hold a stock, in that case you can sell a stock. In that case, your profit is your function I plus 2 and then false. So in that case, if hold, then you sell a stock. And then when you sell a stock, you gain the prices. So you gain the prices I after you sell a stock. So you add this one to the profit. Else, if not hold, in that case, you purchase a stock. If you purchase stock, then you use this prices I, so you minus this price I, and then in that case is equals the next state is I plus 1, and then that is true. So when you enter the next, you can enter the next day, and then your hold status is true because you just purchased a stock. So in that case, so what is our answer for what is our output for this function? That is the maximum from both answer 1 and answer 2. So return the maximum of answer 1 and answer 2. So basically, there are two different scenarios. Scenario 1 is you do not do any transaction. In that case, your total profit equals the profit you get from the next day. And then for this scenario 1, whether or not you hold the stock, you can choose to perform to do no transaction. So it's independent of your hold status. You just carry this hold value to the next state. The second scenario is you can do a transaction. So in that case, you can purchase or sell. Whether you purchase or sell depending on your hold status. If you hold a stock, then you can sell the stock. And then after you sell the stock, because you need to have a cool down for 1 day after you sell a stock. So in that case, the total profit is the price I, what you will gain after you sell this stock. Basically, the prices you are selling this stock, and then plus what the profit you are earning from I plus 2 day. If you do not hold a stock, then you can do the transaction to purchase a stock. And then when you purchase a stock, you use this prices of I. So in that case, you reduce that from your total profits. And then for the profits of the ith day, you just return the maximum of the two. So that's the recursive function. So let's run the solution. Oh, so we forgot to call this a recursive function. So basically return function. So our starting point, so how we call this function, we call it from you are on the 0 step. You are actually on the first day. That is when the index is 0 in the prices array. So in that case, your hold equals false. You do not have any stock at the starting point. So let's run the solution. Okay, we passed the two simple test cases. Let's try submit it. You are most likely to run into the time limit exceed error. Okay, yeah, it's as expected. When you try to submit the solution, the time limit exceed. So why is that? So in that case, let's analyze the time complexity and then also our space complexity. So the time complexity is actually O2 to the power of n, and our space complexity is On. So how to optimize this recursive solution? So a common technique to optimize the recursive solution is to use memoization. So in that case, we try to reduce the time complexity to On. how to achieve that? So basically by remember the value we encountered before. So in that case, you keep track of the values you encountered before. So in that case, let's try to take this solution and then modify on top of that. So in that case, we want to keep track of we have a dictionary, or we can call it memory. That is our dictionary. We want to use this dictionary to keep track of the values we already calculated. So we keep base case the same. And then after the base case, so basically let's check. If I hold in the memory, we just directly return memory I hold. So that is if its hours has already been calculated before, which means we already stored it in this memory dictionary, then we just return it instead of like entering the recursive, calling the recursive function. And then if it's not in the memory, if it's not calculated before, we just start our calculation. So in that case, our memory I hold equals the maximum of those two. And then we just return memory I hold. So basically after calculation, we put the calculated value in our memory and then we just return it. Now let's run this improved solution. Okay, we passed the basic test cases and let's try submit it. Okay, so this solution actually passed. So compared with our original recursive solution, we use the memoization. Basically, we add a memory dictionary to keep track of the values we have already calculated before. And then our base case remain the same. It just we add one step. We first check if it has already calculated before. If it's calculated before, then we retrieve that from the memory dictionary and return the value directly. If it's not calculated before, then we just calculate as how we did in the recursive solution. And then after calculation, we just store this value in our memory, and then we return the value. So that's kind of how we improved on top of the recursive solution. And then now I'm going to cover how to solve it using dynamic programming. So to solve it using dynamic programming, so we want to have a dynamic programming array to actually keep track of the status for each day. So in that case, what we are trying to have is actually a array with to represent each day, and then also the hold status. So we initialize that to 0, so the profit is 0 at the very beginning. So 0 for so basically we want to have something dpi and then hold status. So basically similar idea to how we did that in memoization solution. So in that case, we have a function with input I and hold. Here we want to keep an array to have the status to keep track of I and hold. So and then when we initialize that, so this one represents the hold. So in that case, we choose from 0, 1, and then this one we are actually extended beyond the original length of n. We add 2 more elements. Why is that? Because let's think about that. If we are on the dpn minus 1 on the last day, and then in that case, that is actually need to determine if we, let's say for currently when I equals n minus 1, and then we are calling the next is actually n minus 1 plus 2 or n minus 1 plus 1. So in that case, that's why we need to add 2 to this one. So to make sure we are not going out of we are not going out of index. So that is our array for our dynamic programming approach. And then let's try call this and then filling in the value. So in that case, for I in range n minus 1, minus 1, minus 1. For hold in, actually hold have 2 options. It's either a 0 or either is 1. So in that case, our dp I hold. So similarly, answer 1 equal answer 1. So equals dpi plus 1 hold. And then if you are hold, basically you are having 1 stock. In that case, your answer 2 equals dp I plus 2 and then false, which is 0. And then here we are considering selling a stock, sell a stock. And then previously there is no transaction. That is prices I. That is what you gain by selling 1 stock. And then after you sell a stock, you enter a cooldown period. Else, if you do not hold the stock, you just purchase. And then after you purchase the stock, your hold status becomes 0, becomes 1. and then in the end you just return dp0 and 0. So before you return the final solution, you actually have to assign that. Basically, inside this loop, you are trying to calculate dpi hold. That is the maximum from answer 1 and answer 2. Okay, n is not defined, so n equals the length of prices. So this solution also passes all the test cases and is also accepted. So my dynamic programming approach actually looks very similar to the memoization approach. Here I'm just using an array to actually store, I call this dp, to actually store the status. And then while trying to loop it through, I start from the very end. Why? That is because for dpi hold, that is actually determined by dpi plus 2, 0, dpi plus 1, 1, and then also dpi plus 1 hold. So that's determined by the later days. So in that case, that's why we are trying to loop it through. We go we calling the I for the range n-1 and up until I reach 0. So that's our dynamic programming approach. So in that case, the time complexity, similar to the memoization approach, the time complexity is still O(n), and then space complexity is also O(n). So next, I'm going to talk about how to optimize the space complexity on top of this dynamic programming approach. So basically, optimize the space. So let's take another look at our dynamic programming approach. So in the dynamic programming approach, we are trying to calculate the dpi hold. That's what we are trying to calculate. And then in order to calculate this one, what we need? So we need to know dpi plus 1 hold. We also need to know dpi plus 2, 0. We also need to know the dpi plus 1, 1. So we need So that's what we need in order to calculate the dpi hold. So in that case, you can tell from here, so basically dpi is not determined by dpi plus 3. It's only determined by dpi plus 1, dpi plus 2. So in that case, we can optimize this dynamic programming approach. So to optimize that, so we want to save more space. So we want to have a smaller array to actually store the dp value. So in that case, for each I day, we only need I plus 1 day and I plus 2 day. So in that case, we only need to know I plus 1, and I2. So we need to keep track of those 3 days. So in that case, we can just reduce this one from n plus 2 to actually to 3. And then in that case, we are still trying to loop through, we keep the same for loops. And then it just, when we keep track of the state, let's say, instead of keeping track of the original I, where I is from n minus 1 up until 0, we just mod 3. So basically, compared to the original dynamic programming approach, we modify the array. So that's, in that case, our DP, the dimension for our DP is 2 times 3 instead of 2 times n plus 2. That's the first modification. And then the second modification, since we're for the day, for I, we only keep track of the 3 different states. So we just like divide it by 3 and calculate the remainder. So that's kind of the modification we are making. And then let's run this solution. So you can tell for this one, the space is actually optimized. So for this solution, the time complexity is still O1. That's something you can easily tell from those 2 lines, the for loop. And then the space complexity is actually optimized to O1 because you only need an array of dimension 3 times 2 as opposed to n plus 2 times 2. So in this case, you optimize the space for this dynamic programming solution. So for this problem, I went over how we actually start with the recursive solution that exceeds the time limit, and then how we optimize that using memoization. Basically, we have a dictionary to store the values we already calculated so that we do not to repeatedly calculate the same thing. And then we also talk about the dynamic programming approach. It has the same time and space complexity, that is O(n) and O(n). And then we also talk about how we optimize the space complexity on top of the dynamic programming solution.